Today we will discuss the reactivity series of metals towards oxygen and its application. Different metals have different reactivity with oxygen. More reactive metal will burn rapidly and burn more brightly in oxygen, while less reactive metal will burn slowly or only glow in oxygen. Most metal form metal oxide when heated or burned in air. For example, when magnesium is burned in oxygen, it will produce magnesium oxide. And since magnesium gains oxygen, magnesium undergo oxidation and act as reducing agent, while oxygen will undergo reduction and act as oxidizing agent. Now, based on the chemical reactivity of those metals with oxygen, the metal can be arranged in a list from most reactive to the least reactive, and we call this series reactivity series of metal, where metal in higher position is more reactive while metal in lower position is less reactive with oxygen. Potassium, sodium, calcium, and magnesium burn vigorously with oxygen. Aluminium, zinc, iron, tin, lead, and copper will only glow when reacting with oxygen, while mercury, silver, and gold do not react with oxygen under normal condition. The reactivity of metal with oxygen is closely linked to its power as a reducing agent. Note that the metal at top of the series easily lose their electron. These metals are good reducing agent. On the other hand, the metal at the bottom of the series are poor reducing agent, as they do not release their electron easily. Therefore, the reactivity series are also lists of metals according to their strength as reducing agent. In this experiment, the metal powder is heated in the presence of solid potassium manganate. The potassium manganate will decompose when heated to produce oxygen, and the oxygen will react with the metal powder. Glass wool is used to separate the metal powder and the solid potassium manganate. This is because if the metal powder and the solid potassium manganate are mixed together, the mixture will explode when heated. Now, by observing how vigorous the metal react with oxygen and intensity of the flame or glow, we can arrange the metal based on their reactivity with oxygen. Based on this observation, we can conclude that magnesium that burns very rapidly with very bright flame is the most reactive, followed by zinc that burns rapidly with bright glow, followed by iron which burns less rapidly and the glow is less bright than zinc, followed by lead that burns slowly with a very faint glow, and finally copper is least reactive because copper only displays faint glow in oxygen. Now let's look at the color of the oxide when hot and color of the oxide when cold. Only two metal oxides have different color when hot and cold, whereby zinc is yellow when hot and white when cold, and lead is brown when hot and yellow when cold. The rest of the metal will have the same color of hot or cold oxide, whereby iron oxide is reddish brown, copper oxide is black, and magnesium oxide is white. Next, we are interested to discuss the position of carbon and hydrogen in the reactivity series because just like metal, carbon and hydrogen are also good reducing agent and form oxides. Carbon is located between aluminium and zinc, while hydrogen is located between zinc and iron. Since carbon is located below aluminium in the reactivity series, carbon is less reactive than aluminium. Since zinc is below carbon in the reactivity series, carbon is more reactive than zinc. Hydrogen is located below zinc in the reactivity series, so hydrogen is less reactive than zinc. But since hydrogen is located above ion, hydrogen is more reactive than ion. The reactivity series are very similar to the electrochemical series because both are related to the ability of metals to lose electron or their strength as reducing agent. However, the position of hydrogen in electrochemical series and in reactivity series are different. In reactivity series, hydrogen is located between zinc and ion, while in electrochemical series, hydrogen is located between lead and copper. The position of carbon in the reactivity series can be determined based on 1. The ability of carbon to remove oxygen from metal oxide, and 2. The ability of metals to remove oxygen from carbon dioxide. When carbon is strongly heated with a metal oxide, if carbon is more reactive than the metal, the carbon can remove oxygen from the metal oxide. Or in other words, carbon can reduce metal oxide to metal. However, if carbon is less reactive than metal, carbon cannot remove oxygen from metal oxide. For example, carbon can react with zinc oxide. This is because carbon is more reactive than zinc. Therefore, carbon is able to act as reducing agent, removing oxygen from zinc oxide. However, carbon does not react with magnesium oxide because carbon is less reactive than magnesium. On the other hand, if the metal is more reactive than carbon, the metal can remove oxygen from carbon dioxide. In other words, metal can reduce carbon dioxide to carbon. However, if the metal is less reactive than carbon, metal cannot remove oxygen from carbon dioxide. For example, magnesium burns in carbon dioxide to form magnesium oxide and carbon. This is possible because magnesium is more reactive than carbon and therefore can remove oxygen from carbon dioxide gas, or magnesium act as reducing agent to reduce carbon dioxide to carbon. However, hot zinc will not react with carbon dioxide since zinc is less reactive than carbon, or zinc is located lower than carbon in the reactivity series of metal. So let's discuss the experiment to determine the position of carbon in the reactivity series. When carbon is heated strongly with the metal oxide, carbon can act as reducing agent to remove oxygen from the metal oxide if carbon is more reactive than the metal, or if carbon is located in higher position in the reactivity series of metal. When carbon reacts with zinc oxide, a gray solid is formed to indicate that zinc is formed, or carbon managed to remove oxygen from zinc oxide to form zinc. When carbon reacts with copper oxide, brown solid is formed to indicate the formation of copper, and carbon managed to remove oxygen from copper oxide to form copper. However, when carbon reacts with aluminum oxide, there is no visible change, indicating that carbon is unable to remove oxygen from aluminum oxide because carbon is less reactive than aluminum. So we can summarize that carbon is more reactive than zinc and copper, but less reactive than aluminum. Next, to study the ability of metal to remove oxygen from carbon dioxide, a heated metal is placed in carbon dioxide. For example, when a piece of magnesium ribbon is heated and placed in a gas jar filled with carbon dioxide, the magnesium ribbon burns brightly, producing white residue and a lot of black powder on the wall of the glass jar. The white residue indicates the formation of magnesium oxide, while the black powder on the wall of the glass jar refer to the formation of carbon. So magnesium acts as reducing agent to reduce carbon dioxide to carbon. Next, we can determine the position of hydrogen in the reactivity series based on the ability of hydrogen to remove oxygen from metal oxide. To do this, a metal oxide is heated in the presence of hydrogen gas. If hydrogen is more reactive than the metal, hydrogen is able to remove the oxygen from the metal oxide. In other words, hydrogen is able to reduce the metal oxide to its metal, while hydrogen itself is oxidized to water. On the other hand, if hydrogen is less reactive than the metal, hydrogen is unable to remove the oxygen from the metal oxide, so no reaction will take place. For example, hydrogen can reduce lead oxide to lead, while hydrogen itself is oxidized to water. The reaction is possible because hydrogen is more reactive than lead metal, or hydrogen is located above lead in the reactivity series of metal. On the other hand, hydrogen does not react with zinc oxide, as hydrogen is less reactive than zinc, or hydrogen is located below zinc in the reactivity series of metal. Now let's discuss the experiment to determine the position of hydrogen in the reactivity series. In this experiment, the metal oxide is placed in a porcelain dish and placed in a combustion tube, whereby the combustion tube are constantly connected to dry hydrogen gas to remove all air in the tube. The hydrogen is produced from the reaction between dilute sulfuric acid and zinc in the presence of copper to sulfate solution as the catalyst. The hydrogen gas will then pass through anhydrous calcium chloride to dry the hydrogen gas. Next, the metal oxide is heated strongly and any changes is observed. The flow of hydrogen gas should be continuous throughout this experiment to prevent the oxidation of metal back to metal oxide. When hydrogen reacts with copper oxide, a bright flame is produced, whereby the black powder changes to brown. This black powder is the original copper oxide, and when it changes to brown, indicate the formation of copper, or hydrogen managed to remove oxygen from copper oxide to form copper. When hydrogen reacts with lead oxide, a bright flame is produced, and the yellow powder changes to gray. The yellow powder is the lead oxide and gray is the lead metal. So hydrogen managed to remove oxygen from lead oxide to form lead. When hydrogen reacts with iron 3 oxide, a bright glow forms and the brown powder changes to gray. The brown powder is the iron 3 oxide and the gray solid is iron metal. However, when hydrogen reacts with zinc oxide, no glow is observed and the white powder becomes yellow when hot and white when cold. So this is the characteristic of zinc oxide, so there is no reaction occur. From the observation we discussed, we can conclude that hydrogen is more reactive than copper, lead and iron, but less reactive than zinc. So we can conclude that hydrogen is located above copper, lead, and iron, but below zinc in the reactivity series. So aside from predicting the reaction of metal oxide with carbon or hydrogen, the reactivity series of metal towards oxygen can also assist us in predicting reaction involving metals. For example, displacement of metal from the metal oxide. If metal X is more reactive than metal Y, metal X can remove oxygen from oxide of metal Y to form oxide of metal X and metal Y. Next, we can deduce whether metal can react with steam or water in gaseous form. whereby if metal is more reactive than hydrogen, metal can remove oxygen from water to form hydrogen gas, and the metal will form metal oxide. Next, we can predict whether the metal will react with carbon dioxide, whereby if the metal is more reactive than carbon, the metal can reduce carbon dioxide to carbon. Next, we will discuss the application of the reactivity series in the extraction of metals. Very few metals are found in their free elemental state. Most metals are obtained by extracting metals from ore, which are naturally occurring rock containing high concentration of the metal compound. For metal higher than carbon in the reactivity series, potassium, sodium, calcium, magnesium, and aluminium, which are very reactive metals, the extraction must be carried out by the electrolysis of molten metal compound. For metals lower than carbon in the reactivity series of metal, such as zinc, iron, tin, and lead, which are fairly reactive metal, the metal ores reduced by strong heating with carbon in a blast furnace. Carbon is chosen as the reducing agent because carbon is relatively cheap, widely available, and the waste product is carbon dioxide, which is non-poisonous and can be released directly to the air without further treatment. Less reactive metals such as copper and mercury are reduced from the ore by heating directly in air, while less reactive metals such as silver, aurum or gold, and platinum exist as uncombined elements in earth crust as grain or nugget. In fact, gold is the first metal discovered by man because gold is found as free metal in nature. Iron and tin ores can be found in Malaysia, and the extraction of these two important metals will be discussed. Iron are usually obtained from hematite Fe2O3 and magnetite Fe3O4. The extraction of iron involves the reduction of the ore by carbon in the form of coke. Coke refers to carbon made by heating coal in the absence of air, and it contains 80% of carbon. The reduction of iron ores by carbon occurs in a blast furnace. First, the furnace is loaded with three raw materials from top, which is concentrated iron ore, coke, and limestone. Next, hot air blast is forced up the furnace from the bottom. The oxygen in hot air reacts with carbon in coke to produce carbon dioxide, and this carbon dioxide will react with carbon to produce carbon monoxide. Next, the carbon and carbon monoxide produced will reduce the iron oxide to iron. Next, the molten iron is collected at the bottom of the furnace and it is drained off periodically into mold and allowed to cool to produce cast iron. The limestone added will decompose when heated to produce calcium oxide, CaO, and carbon dioxide. This calcium oxide will react with silicon dioxide, which is sand impurities in the ore, to produce calcium silicate, CaSiO3, or slag. Molten slag is less dense than molten iron, so the slag will float on top of the molten iron and protect the iron from oxidation by the hot air. The slag is also drained off at regular intervals. So next, let's summarize the extraction of iron. First, three raw materials loaded from the top of the blast furnace, which are iron ore, coke, and limestone, and blast of hot air from the bottom of the furnace will convert carbon to carbon monoxide and carbon dioxide. The carbon dioxide will be the waste gas. The iron oxide will be reduced by carbon and carbon monoxide to molten iron, and the molten iron will be molded into cast iron, whereby the cast iron still contain 5% of carbon and can be converted into steel in oxygen furnace. The slag waste product produced during extraction of iron is mainly used for road surfacing, and the slag can also be used for the production of cement and building materials. Last but not least, we will discuss the extraction of tin, which is very similar to the extraction of iron. Tin is extracted from cassiterite ore that contain tin 4 oxide, SnO2, as the main compound. First, the cassiterite ore will be crushed and washed, and the minerals will be concentrated by trapping the minerals in floating form. The mineral will then float on top while impurities such as soil particles will sink at the bottom. The concentrated minerals will be roasted in air to convert tin sulfide to tin oxide, and impurities such as sulfur, carbon, and oil will be burned off. The tin oxide, together with coke and limestone, will be heated in blast furnace so that the tin 4 oxide will be reduced by carbon and carbon monoxide to tin. Carbon dioxide will be released as the waste gas, while the molten tin that sink at the bottom will be drawn off and molded into blocks of tin. Calcium oxide from the decomposition of limestone will react with impurities such as silicon dioxide to form calcium silicate or slag. Aside from tin and iron, copper, gold, and bauxite, which is ore of aluminium, are also mined in our country. Historically, our economy once relied greatly on tin industry because our tin reserve is among the largest in the world. However, nowadays, tin industry plays a smaller economic role due to depletion of reserve. That will be the end of our lecture today. Thank you, and please remain at home as our government just extended our movement control order to the 4th phase.